The basic source of error in Euler's method is that the derivative at x of I, or the beginning of our interval, is assumed to apply across the entire interval. That is x of I to x of I plus 1. Hume's method improves this by using the slope at xi plus 1. And it uses a predictor-corrector scheme to improve our estimate of y at the next point. So that is, we have a predictor where y of I plus 1, it's going to label it 0 because it's the 0th iteration, is equal to y of I plus our derivative at xi and yi multiplied by our step size h. Then we come along and we correct this by saying our new estimate of I plus 1 is equal to y of I plus the average of the slope at x of I and the slope at x of I plus 1 and y of I plus 1 at our predicted y plus 1 value multiplied by h. In short, the corrector can then be iterated because it includes y plus 1 in both equations. So we could rewrite this to say, in general, y of I plus 1 to the n plus 1 correction is equal to y of I plus a half multiplied by the derivative at our xi, yi plus the derivative xi plus 1, y I plus 1 for the nth prediction multiplied by our step size h. So perhaps it's easier to view this in the graphical sense. Essentially what we're saying is that if we had some graph, let's say it looks something like this, and we are at the beginning of our interval, xi, we calculate the slope at this point, and we shoot out to this point here, which has our predicted value of y I plus 1 at point xi plus 1. We then calculate the slope at this point now. I'm going to draw a parallel up here. And then we average between the blue and the green slope to get a new correction. Let's draw this in yellow. Of our next point. So this is now the corrector. All right. And then for ODEs of the form y prime equals f of x, we only use the corrector. That is, y of I plus 1 is equal to y of I plus the average of f of xi plus f of xi plus 1 divided by 2 multiplied by our step size, h. And a last note on errors, the local truncation error is of order step size cubed, and the global truncation error is of order step size squared.